So, anybody ever heard of the band Kraftwerk from the 1970s? Yeah, you heard of it. So they did a song, there was an album called Radioactivity, It's in the Air for You and Me. And they actually send that in Morse code during the first song on the record. And you also recently think about Fukushima Daiichi Genpatsu, the reactor that had a recent explosion, which is sort of near and dear to my heart because I lived in Japan for many years and I go there quite frequently. So there's that side of it, but we live this radioactive life where there's radiation around us all the time happening. You eat food that has radioactive elements in it. If you've ever eaten bananas, they're loaded with potassium-40, which is always decaying in your body. If you've ever eaten Brazil nuts, they're quite radioactive. They're full of radium. You know, the stuff that was on the dials in your watches that glowed in the dark back in the 50s and 60s. It's in your home if you have a granite countertop, or if you have a smoke detector, an ionizing style smoke detector, it's in your house. You never know where you might find it inside your house, and it's always raining down on us in the sky. So coming down right from the sun, right on us. It's a natural process. It's in everything we do. It's even in your body. And there's 4,400 becquerels of decaying atoms in your body. Every second, that means there's 4,400 decays in your body, roughly, every second, right now, as you're sitting there. Isn't that interesting? Did you know that? No. So, this stuff is happening all the time. So, all right. So, one of the things that's always mystified me is that there's these low-dose things that seem inconclusive. And, you know, people will say these things about low doses of radiation that to me seem really weird in the news. And this story came up just a couple of days ago on March 10th. So here's this guy who's a firefighter in Connecticut, and the police detected weird radioactive signatures. They're driving by, the highway patrol pulls this guy over because he was going click, click, click. Okay? So they pull the guy over and they say, what's going on with you? It turns out that he had a heart condition. And they'd given him a radioactive tracer to trace the blood flow in his heart. And it was that radioactive, okay? And they pulled the guy over and say, what's going on? Well, I had this procedure, right? And so they say, some doctor comments on the story and he says, well, any amount of radiation is harmful, but this is not harmful. So any amount of radiation is harmful, but nobody has shown that this level of radiation has been of significant harm. What does that mean? You know, that's cognitive dissonance. So low levels, we don't know. People live in places where there's a lot of radioactive rock around. People live at high altitudes. I spent a summer in Santa Fe where the radiation levels are quite high and people are not dropping like flies. So something seems a little off here. You live with inadvertent sources in the home. I can detect my smoke detector quite clearly with a scintillation counter. So that happens all the time. People fly airplanes. Pilots are always at elevated levels, and yet they're not all dying of cancer. So we also know that high doses kill. So there's some interesting transition point in there, and I find that really interesting. So also when we talk about this stuff, we also have to treat science very carefully. The science is tricky. This is the radiation chart that came out right around the time of the Fukushima incident. And one of the things that when it first came out, it was really kind of wrong because it talked about dose rates versus doses. So doses are an integrated form of the dose rate. And it got it kind of mixed up. So it talked about how many sieverts per hour sometimes and how many sieverts. And it didn't get those two, it got them all kind of jumbled up. And it still has one thing jumbled up that I don't understand. The very first thing on the chart, it says sleeping next to someone is 0.05 microsieverts. But sleeping next to someone for how long? What does that mean? So science is a tricky business. You have to be careful. What do you mean by that exactly? Or what units are you talking about? Is it sieverts or grays? You know, rems or rads? And it's the same problem when people talk about watts and joules or amps and volts. it's very easy to make some kind of claim and not really be saying anything. So you got to watch out with this stuff. Now let's talk about ionizing radiation and what it means. The idea with ionizing radiation is you have usually high energy photons or high energy particles. And examples of this are X-rays or gamma rays, which are even at higher energy. And the real key here is that it rips electrons off of things. So it hits an atom and it just tears the electrons right off. And this makes distinct chemical changes directly to the atoms. So it allows those to bind to something else, and that will make a chemical bond right there. So that's a real distinct difference from non-ionizing radiation. Non-ionizing radiation is lower energy radiation, like radio frequency stuff. And being a ham, I deal with this stuff all the time. This is RF. And don't get confused by this, it's quite different. This has a major side effect of just heat. It often heats the material, like your microwave oven. It's distinctly different, okay? So examples of this are light, infrared, that kind of thing. And it doesn't directly make changes. Its side effects, it has secondary emission effects that will make chemical changes, okay? Very different. So keep that in mind. When people talk about radiation, you ask, is this ionizing or non-ionizing radiation? Very different thing, okay? Now, how do we produce radiation? There's two basic ways here on Earth that we produce it. There's brimstone, which is called breaking radiation, and there's atomic decay. Now, breaking radiation is how they do it at the dentist's office. This is where you shoot a stream of high-speed electrons, usually, at some target. So you shoot them really fast, and then you stop them all of a sudden. And when they stop, that energy has to go somewhere. So you take something, you shoot it really fast and stop it, and there's a lot of kinetic energy. That kinetic energy is converted into photons, high-energy photons. And those high-energy photons are usually X-ray photons. And this can happen in any, usually in a tube, and like a cathode ray tube. So if you had an old-style color TV or an old-style monitor, this is why they put a little bit of lead in the glass, is to block those high-energy photons that were coming out. Or even if you have a high-voltage electron tube, the same sort of thing would happen. You get a little bit of X-ray radiation from that. And so that's one way of creating high-energy photons. The other way is atomic decay. And this is what we see in minerals around us, certain types of chemical elements that have unstable nuclei. And these unstable nuclei are a result of just the way that things are packed together with the weak and strong nuclear forces inside the atoms. And they just happen to be balanced in such a way that they're not quite happy the way they are. And all of a sudden, they're just sitting there barely stable, and then one pops off, and then the whole thing decays. So we get sort of a little bit of tunneling or a little quantum fluctuation in the vacuum state, and it goes pop, and something falls off. And so that's what we see when we have some uranium or some thorium or radium or something like that, and we get decays. And there are also out in space many things that radiate in stellar processes. Some of them we understand pretty well, some of them we don't understand very well at all. But on the Earth, those are the two major ways that we find things radiating. Now, we classify the way that things radiate in a couple of different ways, and I want to talk about some of them. Maybe you've heard of some of them. We have alpha, beta, gamma, and then a couple of others we'll talk about in detail. So alpha, we have little clusters of 2 protons and 2 neutrons. And they are pretty big things. They're heavy. And so they're these little blobby things that come shooting out of a nucleus. Beta is electrons. Okay? Those shoot out a little faster. And then gamma are photons. Then we have neutrons, which are neutral particles. They're not charged. And then we have cosmic rays, which come out of space, and those can be all sorts of different kinds of matter. Okay? You got that? That's pretty straightforward. So, now these have different penetration properties. Alpha has a tendency to not penetrate very far because it's big and blobby. So you can actually block alpha radiation with a piece of paper. So if you just put a piece of paper up, you can just block it and it won't go any further. Electrons or beta radiation takes something a little denser. So usually a piece of plastic will block beta radiation. So this would probably block beta pretty effectively. So if you have, if you've ever seen tritium lights, so tritium lights are encased in glass and then a little bit of plastic. Tritium is a beta emitter, and then the plastic will block the beta very effectively. Now, you do have a side effect from that. Often those electrons are moving pretty fast, and they'll slam into the plastic, and then those electrons will give you a secondary X-ray emission because they're slamming into the plastic. So you get a little brimstone, and then you get soft X-rays. So if you have one of these trit lights, if you can measure it, it's very hard to measure because the X-rays are very low energy. But you can actually measure soft X-rays coming out of that, and I've measured that. I have a couple of map reading lights that are tritium based, so they're just filled with tritium gas, and they have a phosphor on the inside, and they'll glow for about 12 years, which is really amazing, 12 years. But they do emit soft X-rays, okay? Now gamma are those soft X-rays and other things that emit at much higher energy, and they will go through all sorts of things. You have to block them with very dense metals. This is where you get lead shielding or vanadium or some other highly dense metal in order to block those things. But most thin metals they'll go through. And if you have something like a scintillation counter where you have to make it very dark inside, it's not uncommon to have the scintillation counter encased in metal. And inside the metal is a photomultiplier tube. And the X-ray or gamma photons have no trouble getting right through the metal. They'll go right through. And as long as it's fairly thin, no problem. Right on through. And cosmic rays, they'll go through anything. They have such high energy. They'll come right through this building. They're raining right on down on you right this very moment. You feel them? Feel warm? Basking in the glow. It's great. Okay, so now one of the cool things is that energy is released when we get these atoms to become unstable, and we often think about that in terms of huge nuclear explosions, which are very destructive, and that is indeed one of the things that happens. And of course, with every dark side, there is a light side as well, so it's not all bad. We learn from this energy release that we can also do productive things, and that is harness some of this energy in a nuclear reactor. And this allows us to generate electricity and any other motive power from this. And so this is a typical reactor. You're seeing the Cherenkov glow here, and this is from high-speed particles that hit the water medium, and the water's dielectric actually has light, much slower speed. The speed of light is much slower in the water dielectric, and these electrons are coming off and neutrons coming off almost at the speed of light coming out of this reactor. And then they hit this medium where the speed of light is actually much lower than the speed of light in vacuum. And then because of that, it's almost like hitting a sonic boom, creating a sonic boom there, and you get this light, and the light is like a sonic boom, and it glows this wonderful sort of violet blue. Okay? So we can use that to generate heat energy like that, or more directly, in this fashion, we can create batteries, alpha and beta voltaic batteries that capture the energy directly in a semiconductor substrate. So this particular battery in the picture is an alpha voltaic that will last 25 years. And so it has a semiconductor material behind it and a layer to try and keep the alpha particles from destroying the semiconductor, which they can do, and it captures that kinetic energy directly inside the semiconductor material, and it's a great thing to use on spacecraft. So you can just shoot it off into space and let it go. So in spacecraft, this stuff has been used a lot, and medical uses, people have been thinking about using these for a long time because they just last virtually forever. Now, what you want to do, if you want to make something that's kind of cool, is detect these elements. And the way you detect radiation is you look for the telltale sign. The telltale sign is ions. And what ions do is they're charged things. We've ripped an electron away from its nucleus. So we want to find this charged state. So that's the distinct characteristic. There's lots of different ways to do this. And the really interesting thing is that different photons have different energies, and those different energies are detectable. And some ways of doing it do it by looking at different elements that have different ionization energies. That's not one of the ways we'll look at right now, but that is one way to detect it. But the real key is to find the ions. Now, here's one really cool demonstration of how you can see those ions. Okay, this is a movie of a cloud chamber. So you get a supersaturated gas, and as the ionizing radiation shoots through this gas, it actually causes condensation to happen. So this is thoron gas. You're actually seeing the alpha particles shoot off, and also you're seeing secondary decays when you see the V-shaped ones. So you're seeing these things decay, radon to polonium to lead, decaying right before your very eyes. Isn't that fascinating to watch? So that's decaying right before your eyes. Really fast. You can see the short half-life, it's 55-second half-life for the radon, 145 milliseconds for the polonium, for those particular isotopes. And there are more decays beyond that. After that 10.5-hour half-life, it goes to bismuth, and then there's another quick decay after that. So this is a huge decay chain, but it's really, really fascinating stuff. Now, you don't necessarily want to make a cloud chamber because they're kind of painful, but one of the things you can make yourself is an ion chamber. Ion chambers are really easy to make. Now, the idea is that these things make this ionized path. That's a current conduction path. And all you need to do is detect this current. It's a very, very small current. So you need something very sensitive to detect it. And to do that, you either need a very low gate current FET, an instrumentation field effect transistor, or maybe a very good Darlington, low leakage current. So very low base current. So as you see, the schematic here is pretty straightforward. You need about 50 volts, so something on that order, 40, 50 volts. And you can see the base of the Darlington is in the probe inside, just a can. You seal it if you can get it really dry inside because they're affected by humidity. And then just put it in your source and you'll see the current rise. It's that simple. There's plenty of demos on the web, okay? Just any can. If you can get a CDV 715, those things are not sensitive at all. They're terrible. You'll be dead by the time the meter moves, okay? They're really, really not useful, but you can rebuild it. So you take the can apart, throw the electronics away, put your own probe in there, dry the thing out a lot, put it back together, maybe put some foil on the outside so that you can get more electrons for there, for example, for beta, and then put an instrumentation FET on there. And I've seen them rebuilt and work really, really well. And that's a picture of one that a guy rebuilt with the foil on the bottom, and it's very, very sensitive. So that's your easiest detector to rebuild, okay? The next thing is your very typical, and there's plenty of kits on sale here, and you can also see them in operation down here, is the Geiger Muller tube. These are based on basically making a spark chamber kind of fail. So you fill a tube with, and I actually have one here. This is a Geiger Muller tube. They're kind of tiny. And you fill it with one of the noble gases, like neon is pretty popular. And when an ion goes through this tube, it ionizes the path, and it has a tendency to stay ionized, and that's the problem. Then they put some halogen gas in here, and that tends to collapse the ionization. So it gets ionized, and then it becomes unionized, and this makes them sort of like an avalanche device. So they go ionized and unionized, and that means you don't get to detect the energy. So bam, bam, and that's it. So you can get the counts, and then that's all you get. So you can't detect any energy. And the problem with these tubes is, if you're going to use them for anything serious, is they can overload. And then they'll get to a point where they'll stop counting if you're in a really high radiation field, and then you're going to find out that you're in serious trouble, and you're going to think that you're not. That's no good. Okay, so this one is also an alpha window tube. I don't know if you can see it, it's pretty hard, but there's a window on the end, and that allows alpha radiation to come through. Otherwise, it would never make it through the metal on the side of the tube. The really cool kind is a scintillation counter, which uses a photomultiplier tube. I have one here, and scintillation material, which glows in X-rays. It uses secondary emission. The photons come in, and it avalanches, and the photons come in and gets turned into other photons. So this is some scintillation material. This is polyvinyl toluene, and you can see it's sort of glowing purple. If I illuminate it with ultraviolet, it really glows brightly, and if you take it out in the sunlight, it glows. But this will glow with radioactivity, and I'll show you the parts I'm using to build a scintillation counter right now. But the photomultiplier, you put it all in the dark, it amplifies single photons. And you can actually detect the energy and figure out the isotopes using something like that. There are semiconductor detectors. The real trick is to keep them from destroying themselves as the radiation comes in. And you can see there, the white dots on that picture are from an X-ray machine. And you can even do it with your iPhone, but I'd be really worried that I would be breaking the camera, because it will destroy the imager. So if you build your own, there's plenty of Geiger counter kits out there. You probably see some of them here. Almost all the tubes, like this one, are from LND in Long Island, where I grew up. They're great tubes. Some of the Russian tubes are not so good. It depends. Many of them have Arduinos on them. You can have a lot of fun with those. Watch out for some of the kits. This particular kit I had to help a friend redesign because the analog design was just so crummy. So not all kits are equal. So watch out. But of the Russian tubes, the SPM-20 is an okay tube. All the other tubes are crap, frankly. If you build a scintillation counter on eBay, you can get these little packages sometimes. This is a BGO crystal. You can get these. These are nice and dense. I have this nice Hamamatsu dual photomultiplier tube, little optical grease, 1800 volts, and you're in business. Build a little detector. It's very easy to build. Light tight enclosure, and you're on the air. Very, very nice. So what can you use these things for? All sorts of fun stuff. Detect radioactivity. Look at the background fluctuations. See what's going on. You can look for more Fukushima fallout. There's cesium-133 that you can detect. It has a long half-life of 33 years. So you should still be able to see it if you have a sensitive enough detector here and there. Look around your house. There's all sorts of stuff. Americium in your smoke detector. There's granite. You can look for your bananas, which are radioactive, and look for the Brazil nuts. You can see it. It's there. Look for other things. You never know what you'll find. You can look at shielding stuff with plates of aluminum foil, see how much it attenuates. It's very, very interesting. Look for some hot rocks. You can. These guys used to prospect with that Precision 111B, which you can see mine is over there, and used to hang it out the car and look for uranium as you drove down the road. You can still do that. Very easy to do. And look for old clocks, lenses, and with thorium coating, and depression glass. Fiesta ware is quite radioactive. You can get that too. So, in conclusion, radioactivity, it's a natural process. It's everywhere. It's going on everywhere. We don't know quite what it does at very low levels to you, but you're in it all the time. So it must be doing something, but it's not killing you at the moment. You can capture it, use it for all sorts of useful things. Build your own detectors. You got stuff here to do it. It's a fascinating area. I love it. It's great stuff. So I'll take any quick questions. We only have a minute. Nothing? Yes. Where do I give this lecture? Right here. I'm going to make an hour-long one somewhere. All right. Well, thank you a lot.